Thank you, organizers, for giving me the opportunity to be here. It's great. And well, I'm going to talk about a subject that has become of prominence in recent years, the fact that we can study quantum gravity effects, genuine quantum gravity effects in the vicinity of black holes close enough to extremality. So that's what I'm going to talk about. My talk is going to be mostly based on two papers that appeared earlier this year. One of them appeared in January. The second one is more recent, and it was together with my student Stefano Trezzi. And well, what's the main question that I want to address in this talk? The question is this one. I think it's a very important one in our field, whether we can observe large quantum fluctuations of the geometry, which I think it's a basic question in quantum gravity. And usually this question is asked in the context of a breakdown that leads to naked singularities. A breakdown of semiclassical quantum field theory in curved space. We know that when you have singularities, then well, this framework breaks down. And if you want to observe it without jumping and committing suicide inside a black hole, then you want to study this in a naked singularity. The problem with this is that, well, these are singularities, so we don't have that strong enough control over them in general. But what we've learned in recent years is that, well, we can have situations where we're in a much better situation, a much better position, because we've understood that close enough to extremality, when you have, say, a black hole with a charge, it also happens with rotation, but I will be mostly talking about charged black holes here. These black holes can have large, but still tractable quantum fluctuations in at least parts of the geometry, a part of the geometry. One of the geometrical modes has large quantum variance. What is this mode that has these large quantum fluctuations? Well, as I'm sure that you know, black holes close to enough to extremality, they develop very long throats. And what's been understood is that the length of the throat, when it's long enough, it has large quantum variance. So it's not a quantity that has a well-defined value in semiclassical gravity. There's an average, there's an expectation value, but there are large quantum fluctuations of it. And this happens even if the black hole is arbitrarily large. You have a very large black hole of galactic size. The curvature is very small, but nevertheless, there are these large quantum fluctuations, and we have techniques that allow us to study them with good control. I'm going to give, in this talk, I'm going to give first kind of an overview of it. Half of the talk is going to be a qualitative overview of the whole picture. Then in the second half, I will go into more of the details. Okay. So, well, these quantum fluctuations, they were first identified or clearly identified in the context of higher dimensional black holes, four-dimensional. That's instead of just two-dimensional. For-dimensional black holes, there was a paper by Luca Eliesio and Joaquin Turiazi a few years ago where they were reanalyzing the thermodynamics of black holes close to extremality, taking into account these large quantum fluctuations. And one of the things that they found is that the density of states of the black hole as a function of energy, E is the energy above extremality, so E equals 0 would be the extremal limit. What they found is that well, at sufficiently large energies, the density of a state is essentially given by the Bekenstein-Hawking entropy, the exponential of it. But there's a scale in these black holes, a scale that I'm going to call EB. B is for breakdown, but it could also be E for quantum, because it's the scale at which the quantum fluctuations become important. This scale for these black holes is a very small number. It's a number that goes like the inverse of the radius, also divided by the entropy. And the entropy of a macroscopic black hole is a very large number, so this EB is a very small number. What they found is that when the energy above extremality hits or reaches this scale, it's as small as this scale, then the density of states is significantly modified away from the semiclassical prediction, and it's suppressed. We get much fewer states than semiclassical prediction would give us. And this is something that is good because we would expect that these black holes, and they are not supersymmetric black holes here, all of this talk, I'm not going to consider a situation where we have supersymmetry or we're close to supersymmetry. There's no supersymmetry inside in anything that I'm going to be saying. Well, the density of these states goes to 0, yes.
You expect in the supersymmetric case doesn't happen this?
So in the supersymmetric case, there are significant differences. Yeah. So in particular, there's a density of states and non-zero density of states at exactly the extremal state, and then there's a gap. So there's a significant difference because, close to extremality, there are light fermion zero modes that modify the picture significantly. I'm not going to talk about that. That would be a different talk, but it's also a very interesting direction in which there's been also lots of progress. So you see that the density of states is much smaller than what semiclassical physics would have us believe. This also affects other phenomena. So this was first identified, but then all of the physics, or at least what this means is that the physics of black holes close to extremality has to be revisited. And one of the things that you have to revisit is how they emit Hawking radiation. This was discussed in a paper last November by one of the authors is over here, I think, Misha. Okay. So this is an impressive paper. It's a paper that, as I told them, it's a paper that takes longer to read than the evaporation time. It's 150 pages. But it's a very impressive paper, and many of the things that I'm going to be saying are based on, or at least were first developed in that paper. So Hawking emission is suppressed in this quantum regime. Yes?
Will you comment why there is the suppression of the interdisciplinary?
Yeah, I'm going to comment on this later. So this suppression of Hawking emission is something that you might expect. You have fewer states, your black hole has fewer states, so then if there are fewer states to emit radiation, then you would expect that the emission should be suppressed. That's, I mean, it's kind of a consequence of this, that you have fewer states, your black hole doesn't have as many microstates as you might think, and then this is going to drive down the emission, the total emission from the system. But we're going to see more of this. Okay, so if your energy is, say, 1/10 of this quantum energy, then you see that the rate of emission per unit frequency is much smaller than the semiclassical prediction would tell you. As I say, this is because you have fewer states that can emit radiation. Now, there's been quite a lot of work on quantum effects near extremality, in particular without supersymmetry. With supersymmetry, or close to supersymmetry, this is an important paper. There have been other more papers. So I'm mentioning here a number of them. For how can you get close to extremality in a black hole? There are different ways. You can have charge, and this was studied in these papers and others. You can also achieve be close to extremality by adding rotation, like in Kerr black holes or in BTC black holes. And there's also more work here, including also people here in the room. Finally, there's a less well-known way of going close to extremality that doesn't involve charge nor rotation. That's in hyperbolic black holes. This is work that I did here with my chairman. My chairman is going to give me 5 extra minutes for mentioning him. So there's lots of developments here. I'm forgetting certainly some references, so forgive me if I'm not mentioning work that you think should be here. But then, so the question is, so we have these black holes close to extremality. They are big objects, but quantum, nevertheless. Say that we're external observers and that we know that we have there a black hole with a given mass and a given charge. That's something that we can measure, say, by measuring Coulomb and Newtonian forces away from this object, and then we see that it's very close to extremality, to extremal bound. How can we make sure that this is actually undergoing all of these large quantum fluctuations? So this is the question. Okay? We're observing this from afar, and then we want to probe this large quantum object and decide that it's really quantum. Well, first, before anyone gets excited about this, I gave this talk a few weeks ago at Harvard, and Seb Dolman of the Event Horizon Telescope was in the audience, and he was asking me, well, I mean, is there any chance that we can observe these things in the black holes that we're taking photos of? Well, I had to disappoint him. Because if you see the numbers, here I told you that the scale, the energy scale at which these quantum effects are important is this very small energy scale, which means that the wavelength of quanta that are going to probe this regime is going to be of this order. Now, if you take an astrophysical black hole, the radius of the horizon is of the order of kilometers or larger. So that's already a fairly large number. It's much longer than the wavelength of the CMB. But the scale, the wavelengths that would be probably in this quantum regime are way, way larger, because this number for a astrophysical black hole is on the 10 to the 80, 10, whatever. And some huge number, something like this, you can very easily find that for a black hole close enough to extremality, don't ask me how you got there, but if imagine that you got there, then this is going to be another ridiculously large number. You're never going to probe this, certainly not with the Event Horizon Telescope. Here I'm not putting the units because it doesn't really matter whether you're using some units or others. Okay, so then, well, the question, this is the question that I'm asking, but I'm asking it as a question of principle, okay, not of practical relevance, and we're doing thought experiments. I think that this is still fine, at least for people in this room. I think that this is a good enough motivation. So how can we observe these large quantum fluctuations? Well, I already told you one way that you can do this. You observe Hawking radiation, you create some charged black hole. Generally, it's going to be away from extremality. Then you let it evaporate until it gets close enough to extremality. This was studied by these people. And then you detect its radiation. But then, well, my joke to them about the evaporation time and the reading time of the article, that was motivated because the time to do this is really painfully slow. It's way, way larger than the age of the universe to, well, some power. Okay? And that's essentially because this is a process of Hawking evaporation. For a large black hole, that's something that's slow. It's a process that when quantum effects are small, when h bar goes to zero, that these are quantities that diverge. And this is further compounded by the fact that, well, close to enough to extremality, as we saw, the radiation is even further suppressed. Okay, so this is not a very practical way. It's something that, you stay there, you're observing the black hole, you're detecting Hawking quanta, you wait a few ages until you've collected 3 quanta, and then you decide, well, they're coming out so slowly that this must be the quantum object. Okay, that's not very efficient, so let me propose something that's, I think it's going to be a more efficient, quicker way. Quicker, in the scales that we're talking about here, okay? So first of all, we want to form the black hole in a faster way. Instead of letting it evaporate until close to extremality, well, we can try to collapse and land on a near-extremal black hole. And then we also want to do another classical observation. Classical experiments are easier to perform rather than fully quantum, so classical formation, classical observation, something that, well, we are classical beings, so it's easier for us to perform that kind of experiment. So we, instead of letting the black hole send us radiation, we're going to send radiation into the black hole and see how the black hole absorbs it. Okay? We're going to do wave scattering. We're going to shine light on the black hole and see what the black hole looks like. So first, let me say a few things about collapse. It's not really important for my talk, but since there was recent work by mathematicians proving that the collapse of a charged matter can be fine-tuned so that, well, you land on what at the classical level would be an exactly classical extremal black hole. And this means that since the process of collapse is finite, then as h bar goes to zero, this is finite time. So this is a fast way of forming a black hole close to extremality. The problem with this, you may have read about this, they say that the third law is violated. I don't like that. I don't like to say that, because actually the third law of thermodynamics only makes sense when we take quantum effects into account. And we've seen that quantum effects tell us that the classical extremal black hole doesn't exist. Why? Because in the extremal limit, in the strictly extremal limit, the black hole has uncontrollably large quantum fluctuations. So as you get close to extremality, the black hole is less and less of a classical object. The saddle point that gives you the near-extremal solution is a saddle point that's broader and broader. So classical extremal black holes don't exist in physics. That's something that I want to emphasize in every talk that I give. Okay, so the classical extremal black hole is not an object in physics. It's a mathematical artifact of taking the wrong order of limits. I think that's something that's important to bear in mind, which means that anything that we knew about classical extremal black holes now has to be, or classical near-extremal black holes now has to be revisited. The correct interpretation of this result, I think, is that you can form a black hole very close to extremality in this quantum regime within a classical time scale. So that's quick. It's a quick way. There's also the caveat here that if you want to prepare your initial data with enough precision, then, well, quantum uncertainty is going to hit you back, and then that's going to take some time to prepare the initial state. But once you have it ready, then you let it go, and it will collapse and form this large quantum object. So that's for formation. Then we want to see the object. We want to observe it. We're going to shine a light on the black hole. We send a wave to the black hole, and then we measure the absorption cross-section. That's the most basic thing that a physicist learns as an undergraduate that you should be doing to observing a system, a physical system. So how do we shine the light on the black hole? Well, you might think of actually going with your torch and then shining it on the black hole. That's not good. You don't want to throw photons following a geodesic to the black hole. And that would be, first of all, that would be high enough frequency, likely that it may destroy the long quantum throat. But besides this, the objection to doing this experiment of throwing photons that are following geodesics, if the photon is following a geodesic, then it's probing the local geometry of the throat. And the local geometry of the throat, most of it is not undergoing large quantum fluctuations. Fluctuations of the geometry of the throat are small, except for the fluctuations that refer to the length of the throat. Okay? So if you are throwing geodesics, and these geodesics are traveling around the black hole and then probing the local geometry, the image that you're going to obtain is just the classical image, the one of the Event Horizon Telescope. Okay? So this is not the way of probing the large, this fluctuating mode. The way to do it is to softly probe it. Yes.
Why did you say that they destroy the long throat?
Well, because if you, I mean, there's only this very little energy above the extremality. So then if you throw something that has more energy than that, then you may still have a throat, but it's not going to be a quantum one. It's not going to be in the quantum regime. You're going to lift the system away from above this quantum regime. Yeah, that's something, I mean, this is something that may happen. I don't really know whether it's possible, but what I'm sure is that in this case, you're not going to be probing the Schwarzian mode, well, the mode that I'm going to call Schwarzian in a minute. Okay. So we want to probe the mouth of the throat. We want to probe it softly. We want to use waves that are low, very low frequencies, and preferably if they are S waves, because this mode is a homogeneous mode. The mode that moves the throat up and down is homogeneous, spherically symmetric. So if you use a massless scalar field, then the S wave of the scalar field is going to dominate the scattering, because these are the S waves are the ones that can get closer to the black hole, that can penetrate closer to short distances. So that's good. The S wave massless low frequency scattering is going to probe these homogeneous fluctuations, so going to couple to this spherically symmetric mode. And then also, if you go to low enough frequencies, then you have very low energy absorption. So you're going to excite the black hole a little bit, but not too much. It will remain within the quantum regime. So then we perform the experiment, and then we compare it with what? With the semiclassical prediction, to see whether the predictions deviate from what semiclassical physics tell us. So you measure the absorption cross-section, and then what should you be comparing it to? Well, the benchmark value here is a result that's been known for decades, that when you consider the massless scalar field scattering of a black hole in the low frequency regime, that's dominated by the S wave, and at very low frequencies, there is this universal result that the absorption cross-section is exactly equal to the area, which maybe it's what you would expect, because in the S wave regime, your wave is probing the black hole equally from all sides, and then since the black hole wants to absorb all radiation that comes to it, then the absorption cross-section becomes equal to the area, exactly equal to the area. So this is the semiclassical prediction, and then this is what we want to see whether it's modified or not when your object, instead of being a semiclassical black hole, is a fully quantum object. Well, fully, I mean an object with a quantum throat, quantum fluctuating throat. So one thing that you may have noticed here, the absorption cross-section is equal to the area. Of course, we know that the area measures the entropy, so you could say that the absorption cross-section is kind of a proxy for measuring the number of states that your system has. because this absorption cross-section is measuring the number of absorbing states that your system has. So we have this result that semiclassical physics tells us that holds, so we could say that, well, if we measure the absorption cross-section, we're measuring the density of states of the black hole as well. Okay? So then, if we have, instead of this semiclassical regime, we're in the quantum regime, what should we expect? Well, I've told you that quantum fluctuations make the density of states much smaller than the semiclassical value. So then, you would expect that if you have fewer states that can absorb radiation, then in the quantum regime, the absorption cross-section should be much smaller than the area, right? Of course, you know that when somebody asks a question, then the answer is no. And it's not a question in the title of my slide. Then, is this correct? No. It was a surprise, I have to say, when I had been thinking of doing this calculation for many months or a year, and then I was all the time thinking, well, I'm going to do the calculation and find that the absorption is much smaller than the area. So in the last Christmas break, I had the time to do the calculation. I did it, and then I found that no, the absorption cross-section in the quantum regime is larger than the area, which means that it's also larger than this density of states. Okay? And it actually gets larger the closer you are to extremality. And I thought, well, this must be wrong. Of course, I rechecked the calculation. I began to dissect it and to see what was going on. So why do we have an absorption cross-section larger than the area, even if you have fewer states that can absorb radiation? Well, the effect here is that, I mean, the absorption cross-section not only depends on the number of states that can absorb the radiation, but also on how efficient they are at inducing transitions, how efficient these states are at absorbing radiation. And it turns out that quantum effects enhance the transitions between individual states, and they can enhance them a lot. So even if you have fewer individual states, they are more efficient at absorbing radiation, and this is what is behind this result. Yes?
I realize I don't understand the question. Isn't there absorption cross-section a function of frequency?
Yes, it's a function of frequency. I have a function of frequency. Then I can also take the... So at all frequencies which are small enough, the absorption cross-section is larger than the semiclassical prediction.
Even at frequencies that are small enough that you can't jump from one state to the next?
So this is something that will come later, but in the...
large enough, okay, sorry.
Yeah. So in the regime that we're considering, the spectrum of the black hole is continuous. So you don't have these gaps. So at least in this case, the gaps in the spectrum, that's something that will appear later. Of course, there's some extremely low frequencies where you can resolve these continuous states into discrete states. That's right. Exponentially small frequencies. This regime, I have nothing to say about.
I see.
Okay, so I'm going always to be in a regime where I'm not discriminating between the extremely fine-grained structure of black hole microstates. I'm not going for that. I would need techniques that go beyond the but that's a good point. But nevertheless, we will see that in some cases, this effect of having gaps in the spectrum that are larger, that's going to play a role. Okay. So these late-time correlations, this is something that has been known because from people, studies of, correlations in JT gravity, in the quantum regime, people have seen that, well, correlations, the two-point correlation function, which in a semiclassical black hole decays exponentially, is the quasi-normal mode ring down, then when quantum effects, which for those of you who know about it, it's still computing things in the disk, in JT gravity, then these quantum effects make the decay, instead of exponential, they make it power law. So it's slower. And that means that late-time correlations, those are low frequency in Fourier space. So these late-time correlations, what they mean is that the black hole is can more easily perform transitions between states at very low frequencies. Now, this was what we found for scattering a massless scalar field. Massless scalar fields, we don't know whether they exist in our universe. What we know is that photons and gravitons exist. So we next studied what happens if instead of sending a massless scalar field, we send a gravitational or electromagnetic wave. And then what we found is that in this case, yes?
The absorption is bigger than the semiclassical one, right? But
In this,
the Hawking emission is less.
Yes.
That's something.
Yes.
It's not perturbed.
Yes, maybe we can, maybe as we go along, these things may become a little clearer, but yes. So essentially, at the end of the day, there's two effects that are competing here. And it's difficult to anticipate which one is going to be stronger. One effect is that you have fewer states. The other one is that the transitions between states are easier, are enhanced. So you have a suppression in the density of states, but an enhancement in the transitions between states. So depending on what observable you're analyzing, what calculations you're doing, then one of them wins or the other wins. And that, without doing the calculation, I'm not in general able to predict. But at least there's this competition. Okay. So Hawking radiation in that case it's suppressed because you have fewer states. Even if maybe I can say something. So when you're emitting a particle, then you're going from some state at some energy to a state at low energy. And then you have at even lower energies, you have even fewer states. So the number of final states is strongly suppressed. If you're absorbing, then you're going from some energy to some higher energy. And then you have more states. So the suppression from having fewer states is stronger when you're going to lower energies than when you're going to higher energies. I think that's kind of the reason behind Hawking radiation emission being suppressed, whereas absorption being enhanced. So, as I said, in this case, what we found is that, we're scattering now a gravitational wave or an electromagnetic wave, and then we found that the black hole can become transparent at low enough frequencies. You don't see the black hole, which is something that, black holes are, if anything, if there's anything that we learn about them, is that black holes are black. They absorb everything that impinges on them. Well, here, in the quantum regime, they don't do that. They can be transparent. In the sense that the cross-section is zero.
Right. I was going to say, is transparent really the right word, or is it more that the wave comes in, gets close to the black hole, bounces off, and never reaches the horizon? It doesn't really go through in some physical sense.
I'm not sure whether, because we're in a fully quantum regime.
Yeah, and you're in some long wavelength regime.
You interact with the object, and the object doesn't absorb radiation.
Right, okay.
Now, how come a black hole can be transparent? It's actually very simple. I mean, it's something that, if you think about it, the thing is that, gravitons and photons carry spin. So when your black hole absorbs a photon or a graviton, it's going to absorb some spin. And spin is quantized. And we're in a regime where the quantization of spin becomes important. So you have a mass gap. So you say that you have the mass of your black hole with zero spin, the completely spinless black hole, and then you consider the mass of the black hole with a few units of spin, j units of spin. This black hole has more energy, rotational energy. Okay? So there's some rotational energy, and this energy, this is quantized. This is discrete. There's discrete jumps. So there are gaps. Okay? So then say that you're sending a photon or a graviton into a black hole that's in the spinless state. Then this photon or graviton must supply enough energy to the black hole to be able to bridge this gap. If the energy is too low, then you don't have any transition to the higher rotational state. Okay? So absorption, if the frequency is below a threshold given by this formula, that absorption is impossible. The black hole doesn't have any state. This is just elementary quantum mechanics, but in the presence of a black hole. Okay? So then this means that your black hole is transparent. You throw some wave, and the wave doesn't have enough energy for the black hole to absorb it. Because in order to absorb it, then it must provide this spinning energy to the black hole. So the calculation, for instance, of the absorption cross-section, in this case, for a photon, the L equals 1 photon, is like this as a function of the frequency. So we have this transparency regime. The absorption cross-section is exactly zero. When you're above this gap, so then the photon can be absorbed, the absorption is not zero, but still it's very much suppressed, because you have very few states. So this is what we call translucency. The black hole can absorb, but much less than the semiclassical regime. Okay? So this is non-zero, but suppressed. Okay, so this is kind of the summary of the talk. Then I'm going to go into some more details, and I think I'm doing very well. Yeah. Keeping Javier happy. something that I always try to do. Any questions? Before I go into the second part. Yeah.
These spin particles
Yes.
is also eliminated there or something?
Yeah, it's also suppressed, and then you also have effects of these gaps in the spectrum, so there's it can get complicated. There's another effect that was considered by Misha and collaborators, which is the emission of diphotons or digravitons, that say that you have two photons entangled in a singlet, spin singlet, so then this doesn't have this gap, but then emitting two photons, that's suppressed. So there's lots of physics here, good quantum physics, if you want good atomic physics, that now we can apply to black holes. But there's no physical, I mean, the only thing that we have to do is think of the black hole as a good quantum system, and then apply the usual rules of quantum mechanics.
So if you try to set up an equilibrium situation, can you deduce the absorption cross-section from the emission of Hawking radiation by the tail balance?
Yes, yes,
I mean, the two calculations are related to each other?
Well, there are relations here. You have to bear in mind that you're away from the thermodynamical limit, so you don't have ensemble equivalence. So you have to be careful with this, but there are some more basic constraints that follow from the tail balance or time reversal symmetry and so on. So all of this is just conventional quantum mechanics. What I'm going to do is always thinking that I'm starting with a black hole of fixed energy, so it's not in an ensemble. You can also consider the black hole is in some canonical ensemble and then consider the evolution. This has been done by some people, but I'm not going to do that. Okay, so let me now go back to these properties of the quantum throats. This idea that black holes close to extremality should behave differently than semiclassical physics tells us, that's something that's fairly old. It was first identified in a paper in the late 80s by this group of people who realized that when the black hole is close enough to extremality, then it has so little energy above extremality that it doesn't have even enough energy to emit a single quantum of Hawking radiation. Your temperature is so low that you don't have energy to emit a single quantum. So then this means that, well, you're in the regime where semiclassical thermodynamics doesn't apply. You don't have large numbers that would allow you to apply thermodynamics. You don't have large numbers of radiation. And then it also means that quantum field theory in curved spacetime breaks down. The emission of a single quantum of radiation is going to change significantly the state of your black hole. Okay? So the fact that quantum field theory in curved spacetime breaks down, then this means that we're in the realm of quantum gravity. And then that quantum effects are important at low temperatures, that's something that shouldn't be a surprise. Go to any lab, any low temperature lab in the campus, and then they will tell you, well, when you go to very low temperatures, quantum effects are very important. You can't neglect them, okay? Particularly if you're going to study the behaviors of thermodynamics and everything, you have large deviations from that. So that's what we're seeing now here, but in the context of black holes. Here, it's also important, these are, I mean, we're considering the black hole as a conventional thermodynamic system or a conventional physics system. Black holes can also be at low temperatures if they are very large fossil black holes, and then these effects are not there. And I leave it to you to explain why this is the case. That you need to be at low temperatures, but here near extremality, where you have your black hole is behaving as a conventional system. So, well, the way that people have studied this regime of black holes close to extremality is, well, these black holes develop a very long throat. As we know, it's a throat that has a geometry that's ADS2, crosses 2. Then, well, by performing, we'll consider only the spherically symmetric modes, which means that you can integrate out the spherical directions. You get a two-dimensional theory. This is a two-dimensional theory that doesn't have any local dynamics. It's only dynamics. It's controlled by the physics at the boundary of the throat. That's where this throat, the mouth of the throat, where this infinite throat, or this very long throat, connects to the asymptotically flat region. Not going to go into details here. There are experts here, people who are much more expert than I am at studying this This theory, it's been a big effort over the last decade. Well, the theory that controls these fluctuations of the mode, how this fluctuates up and down in a homogeneous way, that's called the Schwarzian theory. It's a simple action. It describes as the spherical mode. And one important thing is that, at least to the extent that this is an exactly ADS2 throat, this theory can be exactly quantized, and then you can get results that are not just one loop followed by corrections. The results are one loop exact. That was proven by Stanford and Witten. Okay. So if you now take this theory, this is the action, then you put it in the gravitational path integral. You want to compute the gravitational path integral, including the determinant of fluctuations given by this action. Then what you find is that, well, in the partition function at finite temperature, you have the semiclassical result, the Gibbons-Hawking result, times the determinant of the fluctuation operator to the -1/2. And this is a quantity that, for the Schwarzian theory, it can be computed. There may be other modes, but they are going to be subdominant in their dependence to temperature. Okay, so the leading temperature dependence is controlled by this object. Now, when you do this calculation, well, first of all, this is what you get out of the semiclassical Gibbons-Hawking result. You have the entropy, you have the linear term growing like the temperature, but then this is a factor that famously goes like the temperature to the 3/2. Okay? And you see that when the temperature is very small, then this factor can be very small, suppressing therefore the entire partition function. Okay? And this comes from the quantum fluctuation of the throat. And the effect, as you see, is large when you're at temperatures that are smaller than this energy scale that I told you about. Now, this is the partition function. We can Laplace transform to the density of states, and then you obtain the density of states near extremality. Takes this form. So when the energy is very large, then you recover the standard Gibbons-Hawking result for Hawking result for the density of states, but at energies which are small, then you get something that goes like this since this at very low energies, this is the square root. We've seen this picture before in studies of matrix models, so it's the same thing. This is controlled by the same same physics. Okay? So that's the basics of this, well, the thermodynamics of the black hole, but now we want to do not thermodynamics, we want to probe the black hole through wave emission. Okay. Let me say also that, this is what I did in my paper last January. There was work being done at the same time. It appeared a little later by Anna Biggs, but I think she should be given equal credit as my paper for the studies here. Okay. So well, we want to do this experiment of scattering a wave. We send a wave into the near-extremal black hole. The black hole is parameterized by this energy, and by this energy scale, and by the energy above extremality. Consider this fixed, and then we consider black holes with different energy above extremality. So what do? We send a wave into the black hole. We send waves. There's going to be outgoing and ingoing components. When the wave reaches, so the wave propagates classically or semi-classically in the asymptotically flat part of the geometry, but when it gets close to the mouth of the throat, there it begins to act as a source, something that's sourcing the fields in the ADS2 region. Okay. Those of you who are familiar with ADS-CFT, you know that in this case you can decompose this field close to this asymptotic region of the throat. You can extract an effective conformal dimension. This is what I call delta, which depends on the type of wave that you're considering and on the spin. And then the entire, so the interaction between this wave and the throat, that's something that is described the way that we do it in ADS-CFT. So this is a source at the boundary of ADS, and the response is going to be characterized by, well, the conjugate operator. It's going to be some operator here in the one-dimensional theory here, and that's what's describing, well, as I say, the response of the object to this perturbation that we're applying on the black hole. The black hole itself is described by the Schwarzian theory. Okay, we're considering a regime where all of its dynamics is controlled by this mode that makes the black hole mouth jump up and down. Okay. This was done in a lot of detail, more detail, this propagation of the waves in the paper by me and collaborators. So what are we doing here? What is it that we're doing here when we're treating this scattering experiment? So we're doing is replacing the fields that propagate in the classical throat. Instead of considering the propagation of classical fields in the throat, we're replacing them with an effective quantum theory at the mouth of the throat. This theory also has a semiclassical regime. That's something that we can do, just like we can do semiclassical ADS-CFT using language of a CFT, but still consider semiclassical propagation here. But what we're doing here is we're going to the full quantum theory of the throat. So instead of fields, this photon field or scalar field propagating here, what I'm considering is that, well, the field propagates over here, the field there excites or interacts with the state quantum Schwarzian theory, and when we replace this, well, this is going to, instead of being described by some field configuration or some geometry, the black hole, is described by some state of some energy in the Schwarzian theory. And I'm going to consider that the black hole is in some energy eigenstate. Okay? So that's the idea. Anything that we did with semiclassical wave propagation, now we're doing it by coupling our external fields to this quantum theory at the mouth of the throat. Then, well, you send this wave. It's a wave that's oscillating. These oscillations are going to interact with the mouth of the throat, and they are going to excite it. You're kind of driving your black hole with some frequency, and then the black hole is going to respond by transitioning between states. The black hole can absorb radiation, or it can also emit radiation, stimulated emission. Okay? This is simply something that is induced by the source at the boundary of the S2 region. And then at this stage, everything is just textbook quantum mechanics. It's a perturbation problem in quantum mechanics. We can apply the Fermi-Gordon rule, because the interaction here is weak enough. And then, well, Fermi would tell you that, well, the transition between initial and final state of the black hole, you have initial energy and final energy, that's going to be given by the transition amplitudes, multiplied by the density of final states. The more final states that you have, the higher the probability for making this jump. So we take this, we apply this to the system that we had before. There are some factors here that you have to compute from the wave propagation in the semiclassical black hole background. So you can compute what are the decay rates for absorption and for emission, probability rates. Okay? And then you have relationships like this one, which is general. I mean, this is something that follows just from time reversal. You can compute then the total absorption rate, and then here you have to take into account that the black hole can absorb radiation, but it can also emit radiation through stimulated emission. So you have to subtract that. You have to take both into account. Once you've done this, well, where do you get these factors from? So these factors, these are given by the Schwarzian theory. This is something that people have computed over the last few years. The density of states is what I showed you before. The two-point function, which is what's giving you the transition between states, takes this form, at least for the field, for the state, for the operator that has conformal dimension 1, which is what you get for a massless scalar field, S-wave. So we plug in these numbers into these other formulas that we have here. And then this is the result. Okay? So I computed the absorption cross-section using conventional quantum mechanical formulas, and then I get a result that's given in terms of the energy of the initial black hole, the frequency of the incoming radiation, also this parameter that tells me what the black hole is. Yes?
Sorry, a very simple question. Why do you call that a two-point function? Perhaps it's...
It's the Fourier transform of the two-point function.
Ah, okay.
Okay. So the two-point correlation function, you take the Fourier transform, and this is in frequency space, or in, but it's given, it's essentially the same information. So this is the result. It's not too complicated, something that you can analyze easily. And first thing that you want to do is to verify that, at least in the semiclassical regime, which should be contained as part of your full quantum calculation, that you recover the correct result. And that's something that, well, I verified after obtaining the result, so that when the black hole energy is much larger than the black hole is above this quantum regime, then this formula reduces to the old universal result that the absorption cross-section is exactly equal to the area. All of the thing that you have here collapses to 1 in that limit. It's easy to verify. But then you want to see, well, what are the deviations away from this result? And that's what I did is take this expression, plot it, and then I found that the absorption cross-section over the area is larger than 1. It's more than the semiclassical regime. And larger the closer you get to extremality as a function of the frequency. There's some kinks here, and these are due to the fact that, well, when your black hole is close enough to extremality, then you cannot radiate too much energy because you don't have available energy. You cannot emit. So spontaneous emission, stimulated emission is absent when you cross this threshold. So you see that here, yeah, the absorption cross-section, even at, well, for all the frequency range, is larger than the semiclassical result. And that's when, well, when I saw the result, I had to figure out, well, what's going on here. I was expecting the opposite result. Because what this would be telling you is that, well, you have a density of states that is given by this. But the absorption cross-section here is much larger. So the density of states, the naive estimate for what would be the absorption effect, the density of states underestimates by a lot the absorption near extremality. As I said, this is because, well, when you dissect the result and then you separate the two different effects, the effects coming from transition rates and the effects coming from density of states, you see that, well, the density of states, yes, it's smaller in the quantum regime than the semiclassical regime. But the transition rates are larger in the quantum regime than the semiclassical regime. And then when you combine them, turns out that the quantum emission, or the quantum absorption in this case, is larger than semiclassical absorption. Yes. So there are fewer black hole states, but as I said, they are more efficient at absorbing radiation, and as a result, your black hole, your quantum black hole looks larger. If you expected to have a black hole with this cross-section, then you have a black hole with a larger cross-section. Okay, very good. But what happens when you consider other fields? So that was first a surprise, but then the second surprise is that when you consider the absorption of fields that carry spin, the results are reversed. Okay? And the black holes disappear from sight. I already told you the explanation for this. I'm not going to give too many details. But if you are, so this is the density of states of a spinless black hole with spin 0. And this is the density of states of a black hole that has 1 unit of spin. So you see that there's a gap here. Gap coming from rotational energy. And then if your black hole begins in this state and is going to absorb some energy or some radiation with some frequency, but a frequency that would lie within this gap, then you just can't absorb it. The black hole becomes transparent. Okay, so there is this gap. So this is essentially the effect. And you see that this is something that's very simple and very universal. You're going to also find it in other black holes. Okay, it's just basic quantum mechanics. These gaps in the spectrum, I will mention it later, these gaps are sufficiently large that we can still treat them with semiclassical methods. The spectrum here, it looks continuous because the spacings are exponentially small. This, in this level of calculations that I'm performing, you don't distinguish the discreteness of the spectrum over here. But there are larger gaps in the spectrum, and these ones we can compute and study. So this is for example, I mean, similar to the plot that I showed you before, but for two different energies. So this is the transparency windows. You see that as the energy gets closer to extremality, then the transparency window becomes larger. Then you also have the translucency. I'm not plotting here the results for the semiclassical absorption because it's several orders of magnitude larger. Okay, so the black hole is not fully transparent, but still it's translucent. It absorbs very little. Okay. Coming to towards the end, how general and universal the results are? Well, they are very general and universal. This is something, the results for the massless scalar field, you can very easily generalize to higher dimensions. You just have to change the black hole parameters, the area, this breakdown energy in the absorption cross-section, and then you get the correct results. The results are also valid for static near-extremal black holes in Einstein-Hilbert. I mean, you can consider different black holes. All of this is very universal because the Schwarzian theory appears very universally in when you have ADS2 throats, even in cases where you don't have ADS2 throats, like in Kerr. In that case, it's a little harder to extract, but they are also there. As long as you don't have supersymmetry, supersymmetry changes the picture because you have light fermion zero modes, which are crucial for understanding the effect. And this transparency, as I told you, is something that follows just from the fact that the spin is quantized. And then if spin is quantized, energy due to spin is also quantized, and then you're going to have gaps. And these gaps are going to be in the regime that we can control with these methods. So we also expect that Kerr black holes are going to be transparent at low enough frequencies. Even if the calculations in that case are more complicated, like everything with Kerr, but I mean, the effect should be there. We're also investigating other ways of probing the quantum black hole with sent waves. But you can also use other, well, your fields to probe the black hole in different ways. For instance, the tidal deformability. This gives rise to what's known as love numbers. So then we're studying quantum love. We work with Stefano and also with Pablo Cano and Marina David. And that's, we're still undecided whether quantum love whether black holes can have quantum love or not. The jury is still out there, but we'll figure out. And then, well, as I told you, in the case where you're near BPS, that's also very interesting, and that has been studied in these papers recently. But I'm not going to go into that. Now, let me make a few final remarks. So what we've seen, I think that this study, what it highlights is that black holes are actually genuine quantum systems, okay? And we can probe them using semiclassical techniques. As I said, most of the black hole spectrum is extremely dense, and at the level of approximation that I'm working, you don't resolve this discreteness of the spectrum. This is continuous. But the good thing, the nice thing here, is that you have effects coming from spin that introduce much larger gaps. Gaps that are not exponentially small, but that are go like inverse powers of the entropy. And this is much larger. And these ones are the ones that we can study using techniques like the gravitational path integral. So the in conclusion, the answer to the question that I posed at the beginning, can we observe large quantum fluctuations of the space-time geometry, at least in thought experiments? The answer is yes, because we can measure cross-sections, and then for scalar fields, these are enhanced. For photons and gravitons or fields carrying spin, the black hole is going to be transparent, and these are going to be signatures of large quantum fluctuations of the geometry of the throat. With this, I'll stop and thank you.
So we have time for further questions. Oh, Dimitri?
Let me ask you about the IDS2 cross S2 approximation. So first of all, you should be very close to extremality. You have to be very close to the horizon. And third is a classical result. Do you have any control of using this approximation in quantum theory of gravity?
Yes, yeah, we do have a control. So, I mean, you go too close to extremality, then as long as you're close enough to extremality that the energy above extremality is comparable to this breakdown energy, which is very small, then we do have control. I mean, the geometry, of course, most of the geometry is still semiclassical. When you're at these very low energies, well, there's large quantum fluctuations. The length of the throat is not precisely defined. But yeah, we do have, I mean, the ADS2 region, because in this business of deriving JT gravity, you're not just ADS2, you're considering near ADS2, you're considering the deviations away from this that measure how this throat glues to the asymptotically flat region, but I think that, yeah, that's under good control. Then, well, when you consider fluctuations, then I've kept only the modes that are dominant when the black hole is large enough. I mean, you get an effective theory, so this Schwarzian theory, and the theory also that includes the classical field, this is an effective theory in an expansion for large black hole size, And then I've kept only the leading terms. You also have corrections to this, and these ones, well, one can compute and estimate their effects. These are the leading effects only. But yeah, I think this is under good technical control. Yes.
So you talked about this the spin gap, and you mentioned that also that in that context, it's interesting to consider what happens to diphotons or digravitons. Yes. I'm not sure if you mentioned the result. So what happens if you just so, like scalars, or are they?
So it depends a little bit. So diphotons, if you consider a black hole radiating, then diphotons are going to be emitted because that's a spontaneous emission, and that's been considered. That's suppressed. That's small because emitting two photons is suppressed relative to emitting a single photon. But when it's the only channel, then that's what you're going to have. In terms of the calculation, so instead of using the 2-point function for diphoton emission, you have to consider a 4-point function. So you can imagine that that's going to be a more complicated calculation. And then, well, thanks to people like Misha, Luca, and collaborators, well, we have the results. Yeah, so that's for the spontaneous emission. If you're sending a wave that's polarized and of a given spin, then this wave is not going to have a stimulated emission of diphotons. Yeah. That's going to be suppressed.
But if I send it, has the absorption cross section for a beam of incident diphotons been done? And if so, what does it look like?
It hasn't been done, but it's something that can be perfectly well done. If you're interested, I can ask my student, and he will give you the result tomorrow.
Well, somebody should do it, and then presumably you change the language, and you no longer say that black holes are transparent. They
are transparent to a particular, to a polarized wave of a given
circularly polarized.
Yes. Yeah. If you send say a wave that's some coherent state, but without any specific polarization, then you will have. But that's going to be small. It's not going to be fully transparent, but it's going to be small, the absorption cross section. Yeah, that's a good point. Yeah, and actually we're adding we're planning to send a revised version of the article where we discuss this a little bit more.
So in this case, the semiclassical description of spacetimes and how it's broken or something like that. Yeah. Is there any heuristic understanding on when to expect that, or what is the thing behind?
So that's you're close. At low enough temperatures, that quantum effects are going to be unavoidable. You have these very long throats, then the variance in the position of the throat is very large.
In terms of the geometry, what should I say about this? Is something non-local? Is something non-local thing?
Most of the geometry is still semiclassical. So fluctuations of other modes of the geometry, they are going to be suppressed. It's only this coherent homogeneous mode that has large variance. So if you want to measure what's the length of the throat, and then you perform experiments, quantum experiments to measure that, you're going to get a expectation value, but the variance is going to be large. That's the only mode that we can control in this approximation. Other parts of the geometry are just semiclassical. I'm not sure I'm answering.
Curvature is very small, right?
The curvature is as small as you want, which is something that I think
is going on. Then
yes. Well, it's low temperature physics. Yes, you can have it's like you can have large low temperature physics having macroscopic quantum effects. Go to the next lab next door. You can have superconductors. You can have superfluids. Those are collective systems where at low temperatures you have large quantum macroscopic effects. It's a little bit like that. It's low temperatures that make this low temperatures, and the fact that the system is, you also have positive specific heat, so it's a good conventional quantum physical system. And it's just this mode that fluctuates a lot.
Can I maybe add a question to that? So indeed, at the level, if I would do it at the level of the action, typically you would say that quantum gravity effects have a G Newton in it somewhere, meaning Planck length.
Yeah, so this is not Planck length physics.
And the reason is probably that the Schwarzschild mode, I would assume, again, it's a pseudo Goldstone mode, but it's basically because of a broken soft symmetry. And therefore its coefficient in the action is it's kind of small, and that's why indeed at low temperature the effective H bar in front of that term can become large.
Yes.
Right. So at low temperature, it becomes a strongly coupled mode of the geometry.
Yeah. So it's because it's a Goldstone mode.
Because the Einstein action itself does not contribute to its action.
Yes.
Or at least it's sort of becoming from a broken symmetry.
Yeah.
At least I'm just trying to get an intuition.
Yeah. I think that, I mean, it's roughly speaking what we said. I mean, as you said, it's Goldstone modes, follows from symmetry breaking. You have collective effects, which can be large.
You don't expect that to occur in some other places in the universe. So
well, I don't know. I mean, it would be great if it happened. But yeah, unfortunately, the scales here are not precisely within reach.
Yeah, I think the only other place again is when people talk about the soft modes, the BMS symmetry. That can have similar effects, but.
Yeah, I think that this is still to be studied in more detail. There's some mapping between extremal horizons and Scry, and there's recent work on this. And yeah, I won't comment on this, but I'd like to learn more about that.
So, as someone who hasn't thought about this a lot, I have sort of a naive question.
Yes.
The transparency and translucent property you mentioned is for a spinless black hole. If I consider a spin 1/2 or a fermionic black hole, you wouldn't see these properties?
So you're still going to have, the story is going to be more complicated. I chose this example because it's the simplest one. But in general, you're going to have spin-induced gaps, and then depending on how you're probing the system, if the black hole is a spin, there's going to be still some gaps, but then whether these gaps are going to prevent or suppress some absorption or emission processes, you have to study in a case. But it's not complicated, it's simple physics. It just shows, so if your black hole is spinning, yeah, there's still a gap to the next spin state. So the effect is going to be there very generally.
Okay, but I guess my question was, like, if it was a spin 1/2 black hole, I would imagine it would like oscillate between spin 1/2 and minus 1/2.
Yes, there's lots of fun we had with so in the paper by Luca, Misha, and collaborators, they studied this. When you emit fermions or electrons, then you're going to have transitions between spin 1/2 and minus spin. The black hole is going to jump between being fermionic or being bosonic. That's a fairly complicated story, which is one of the reasons that their paper is so long. But it's, I think it's really very nice, very nice results. And as I say, it's conventional quantum physics, atomic physics applied to black holes.
So maybe we can continue the discussion in the break and come back at 10:30. And let's thank Roberto again.